Okay, let's take this up. So x is some random variable. We don't know anything about x except for what we were told in the problem is that the mean of x is 3. The expected value of x equals 3. Very nice mean 3 random variable. Then we take x and we subtract 3 from it. That makes a new random variable y. What is the mean of y? And everybody said, what did they say? 28 people said 0 out of 47. 12 people don't know. All right, let's see. Other common answers. Just 3. Okay, so 3 would be if it didn't change. The correct answer is indeed 0. So if you said 0, congratulations. The reason it's 0 is because the mean operation is linear. So if you add or subtract things inside the mean, they can come out of the mean. So in other words, the expected value of x minus 3 is the same as the expected value of x minus 3. So when you do the expected value of y, you're going to get 3 minus 3, which is 0. So that's the right answer is 0. I guess almost 3/4 of the people got that. This is when we talked about way back when we defined what expected value is, and how if you do the sum of two things, you can do the mean of the sum or the sum of the mean. It's the same. It goes in and out of expected value. Another way to say that is it's linear. If you've been doing derivatives, derivatives are linear, integrals are linear. We like linear stuff in math. Questions or comments about the first part? Anyone who put in 111 want to say if there's a question? Okay, let's look at the other one. This other one, I think we never technically told you this one, but you have all the information you need to do it. Let's see what you said. So in this one, x, we don't know its mean. We just know its standard deviation, which is the square root of the variance, is 7. And then we take it and we divide by 7. So we divided x by 7. What is the standard deviation of y? So what happens to the standard deviation when you divide by 7? And in this one, you guys said it becomes... Ooh, most people don't know. This is very good. So let's do this one on paper. You have a piece of paper?
Oh, I have paper.
I can use, otherwise I can get the tablet out. But so,
Paper is
fantastic. We're going to learn
You
something.
need a pen.
Pen we have.
What, green?
Sure, green. Okay. So the question is, what is the standard deviation of x divided by 7? That's what we need to do. Equals what? And just like before with the mean, like, okay, before we said the mean of x minus 3 is the mean of x minus 3, and that was 3 minus 3. So this is what we wanted, and this is what we have, and we're going to do the same thing with the standard deviation. We're going to turn what we want, and we're going to manipulate it until we get to what we have. And the thing is, this was the square root of the variance, of x divided by 7. And variance we know how to do. We saw the formula for variance earlier in the course. What is the formula for variance? It is the mean of x divided by 7 squared. Okay, there's more stuff. Let's pretend, I'm going to pretend x is mean 0 for this problem. If you don't pretend it's mean 0, everything will be exactly the same except it's more stuff to write out. So I'm going to pretend it's mean 0, and it won't change much, but it'll make it a little bit easier to work out, and you'll see what's going on. Okay, so far what I've done is I've written out the variance in terms of the expected value square. So the variance of x is the mean of x squared. Normally you have to subtract off something, but in this case you're subtracting 0. You guys with me so far? Any questions or comments? All right, now we're back to the same exact trick that we were using before, is we're doing stuff with the mean, and the mean is linear. So let me take this and move it down here. This is the square root of the expected value of x squared divided by 49. And when you divide a 49 inside the expected value is linear, so you can pull constants in and out. So the E operator is linear. So linear means the expected value of x plus y is the expected value of x plus the expected value of y. And you can do constants. The expected value of 2 times x is 2 times the expected value of x. These are both things we talked about. Of course, you don't do ones that aren't these ones, but these ones are both alive. So, okay. So what does that mean? That means I can pull out a 49 in the bottom over here. And now I have a square root on top and a 49 on the bottom. That's very nice. That's the square root of the expected value of x squared. divided by 7. I took the square root of 49. So it got squared inside, and then I pulled it out and it got square rooted. And finally, I notice this is the variance of x divided by 7. So a whole bunch of algebra operations. This is the square root of the variance, which is the standard deviation of x divided by 7. So a whole bunch of algebra operations to take what we wanted and turn it into what we have. And the punchline is that if you divide by 7 inside the standard deviation, you divide by 7 outside the standard deviation. And why did I show you all this? The point is that it's all coming from this fact that the expected value is linear. So it's not a new fact. It's a fact we've seen before. And we're just using it in a different way through the definition of the standard deviation. Okay, so you have these two facts that when you divide by 7, you divide by 7. But let me answer the original problem. The original problem says, what is, on Mathematize, it says, what is the standard deviation of y? Well, it's the standard deviation of x divided by 7, which in our problem, this will be 1. In our problem. So the standard deviation of y is the standard deviation of x divided by 7. In other words, 7 divided by 7, which is equal to 1. So the correct answer is 1. So if you said 1, 1, 1, you were actually pretty close. So they go 0 and 1. And some people got it. You know, if you said 1, 1, 1, 1, 1, you actually got the right answer 5 times in a row. So very good. Okay. Yes, I'll do that next. But let me see if there's any questions or comments about this thing so far. So adding and subtracting, adds and subtracts, dividing, divides. Yeah?
Why can we assume that x is mean 0?
Okay, I assumed x's mean 0, and it made the steps easier. If it's not mean 0, everything still works exactly the same. So it's a good exercise for you if you're into this stuff to try it and see and make sure that I'm not lying to you and that it really does work. And the secret is, I will tell you, so if x is not mean 0, then what will happen is you'll have that the variance of x is equal to the expected value, not of x squared, but of x minus the mean of x squared. Okay? And so every time I was doing an operation, I was like dividing by 7, you're going to be dividing by 7 here, but you're also going to be dividing by 7 here. And so you're going to have 2 divisions by 7, but otherwise it won't change anything. So it's actually not so complicated, and it's still morally true. I kind of showed you the easy version so you could focus on the important parts. If you want to try it on the hard version, it's a good exercise to make sure you're understanding. You can also just remember the conclusion is that the standard deviation, if you divide by 7 on the inside, you divide by 7 on the outside. Yeah?
So is the standard deviation also linear, or is it just a coincidence that this time?
The standard deviation, it's not linear for sums, but it is linear for dividing by a constant. So maybe this is the conclusion. The conclusion is that the standard deviation is linear for, let's say, I'm going to say scalar products. Scalar products. That means multiplying or dividing by a constant. So the standard deviation, am I off the bottom here yet? Okay. Of c times x equals c times the standard deviation of x. So it doesn't work with sums. Like you can't do this thing, but it does work with this. Great question. Okay. Yeah.
How did you go from like the full thing being square rooted?
Yes.
And then only the top.
Yes. Okay. So I use the property of square roots that the square root of a over b equals the square root of a divided by the square root of b. This is a property of square roots. Great question. Anyone else? All right, so what is the point of this warm-up question? Why are we doing it? This is exactly the reason the operation of subtract mu and divide by sigma, which we learned last class, this explains why that works. So let me show you why that is over here. So if you have x, and the mean of x is mu, and the standard deviation of x is sigma, okay? Let's see what happens to the mean and the standard deviation when we do the operation of subtract mu and divide by sigma. So first operation, I'm going to subtract mu. Subtract mu. So this is the new random variable x minus mu. A good example would be what happens if mu equals 3. That's exactly what we just did. When you subtract mu, mu subtracts from the expected value. So you get the new expected value of the new thing, x minus mu, is going to be mu minus mu, which is 0. The standard deviation does not change. Still sigma. Still sigma. Now let's divide by sigma. Divide by sigma. So now we have this new thing, x minus mu divided by sigma. And we ask, what is the new expected value? X minus mu divided by sigma. That's going to be the old expected value divided by sigma. But the old expected value of this guy was 0. So it's 0 divided by sigma, also known as 0. So by doing these operations of subtracting mu and dividing by sigma, we made sure the mean was 0. Let's see what we did to the standard deviation. The standard deviation, oh, this should say the standard deviation of x minus mu is also sigma. Hasn't changed. And now when you divide by sigma, you get sigma divided by sigma, which is 1. So by doing these two operations, we have taken the variable and we've made sure that its mean 0, and we've made sure that its standard deviation is 1. And if you also know one additional fact, which is that it must be normal, if it's always normal, then it will be the standard normal. So this is like the little extra. If x is normal, then x minus mu over sigma is normal too. This is a fact about normal variables, is that they play nicely with addition and scalar multiplication. And therefore, x minus mu over sigma is the mean 0, the standard normal, the one on that table. It's the standard normal. So that's the mean 0 variance 1 guy. Some people write this like this. They say mu equals 0, sigma equals 1. Some people write it like this. They write a big N and they say 0, 1. That's the same thing. Okay. And this is kind of justifying that operation that you learned last class, where we did an example. This is the sort of mathematical justification for why it works. Question over here, yeah.
Did we also say on Wednesday that x minus mu over sigma is z?
Yes, okay, so this standard normal, we sometimes give it a name. We call it the random variable z. But you know, some people might call it other names. It's a thing about the universe. Great question. For example, I think if we found aliens, the aliens would know about normal distributions, but they wouldn't know about z. So they would have their own name for it, but it would be the same distribution, and they would know about mean 0 and variance 1. Standard deviation. Other questions or comments? Okay, so this is the sort of like the simple math behind the subtract mu divide by sigma rule. And so you shouldn't just memorize it. If you know how these operations work, it's kind of maybe more intuitive to see how things work.
There's one line here, though. This is not a simple proof. This is a third-year math stats proof here.
Sure.
Linear transformation of the
Yes, this is a cool fact.
yeah. It's a fact. Right now it's a fact, but the third year you'll do a
Yeah.
proof.
Fact. Okay. All right. Other questions or comments? Okay, we're going to do more with the normal and these kinds of things. I'm going to turn it over to Gary, who's going to show us some stuff.
Going to hopefully fly in a second here and see. And once again,
I think you have
display
to.
settings.
I think you're going to have to connect and reconnect. Maybe this is the.
See, everything. Okay.
Here,
So
try
that's
plugging in. Plugging in.
God, just a second. Let me just freeze that for a second. Freeze. Okay. Let's escape that. So do that. Back to the slideshow. Intro slide.
Okay, now I think you're good on this one. So
Okay.
if we aren't freezing,
Let's see what happens.
now I think you're good.
Think I'm good, eh? Nope. I
What?
lost that one. I get on that one. And then that's good.
That one's good. That one's not good.
That one's for
We'll make that one the dot cam.
Oh, just a sec. We're about to run out of time.
Oh no.
That would be a catastrophe. Okay, we got that. And let's see, where are we? Now, why is that one doing that?
I don't know. Let's make it the dot cam, and then we'll be happy. There you go. You're very fine on this screen.
It's like, why? Why? Okay. Things won't move. Slides won't move. Why will the slides not move? There, that was, but it should go back.
Yes,
Okay.
it's not working on this one anymore.
It's not working on. Okay, let's go. Let's see what we got.
Well, you're back on this configuration.
Okay, let's just try this again. Over there, display settings won't do the duplicate slideshow.
Can we try it? Let's unplug it.
That's your solution?
Yeah.
And now the mouse is just floating around.
Yeah. So try and restart the slideshow now.
Okay, we'll do that. Don't want to do that. It's got a mind of its own. You see it floats. Stop! Go! Oh, this is a problem. This is a problem. Now what's it done? Okay, it's gone back to there. Let's try this again.
So right now it's duplicating what you have. Is that what you want? Or you want to extend?
I think I want to duplicate. In other words, duplicate is supposed to put the same thing on there that it shows on here.
All right. Yeah, that's what you do.
That's
So
what I'm
good.
doing.
All right.
But it's got to behave. Start from beginning. No, we don't want to do that. Go in here. From current slide. It's fighting. It's fighting. Now look at this.
Ah, there you go.
Yeah, but why is it taking so long?
I don't know.
Okay, let's just see if it will give us display settings. See, look at this. This thing's like moving around like crazy. Okay. There, we got duplicate slideshow. We may be somewhere, people. Okay. You know, the problem is I got to go out of PowerPoint when I go to R,
Yeah.
and that will be a mess.
Well, we can
Okay.
do some things on mine.
Okay, we'll have to give this a try. Okay.
Okay, we're back. Thanks
Okay.
for waiting.
Okay. We have to get some past stuff just to get to where I want
How
to
does
get
this
to.
work? That's what we just answered. Okay, great.
Yeah,
Fantastic.
we went through there. So we did a couple of questions here. This is what I wanted to get at. We did a couple here where we had, let me just move these. We had one with a mean of 60, standard deviation of 10. This is not something you've got to write down, but it's something I need to write down so I remember what I had on my slide. We worked out the probability x is greater than 65 is 0.3085, and the probability x was less than 45 was 0.0668. And we also had this question here, find the value of x naught. Find value of x naught. Such that the probability x is greater than x naught equals 0.90, and we solved that turned out to be x naught equals 47.2. So we worked those out with our tables, doing this by hand. And now what I want to do is try this with this online calculator at StatTrek.
You stay in the thing.
Okay, so
So this was what we did at the very end of last class. We were playing with this. Okay.
Oh, it's working for my computer. It's working for my computer.
But now can we get back in the PowerPoint? Or is this
Well,
is
we'll
this
see.
forbidden?
We'll see. We'll just see what happens.
Okay. We're gonna
Okay. So, is this going to work? I don't know. But, it's the computer equipment. We're not sure whether the computer equipment works. Okay, so it comes up automatically with the standard normal distribution. Notice it's got a mean of 0, standard deviation of 1, and maybe you remember that if we had a standard score of 1.96, this is kind of like one of the magic numbers you just tend to remember. We leave the probability blank. And if we remember what number we should get 0.975. Is it going to give us 0.975? It did, 0.975. Similarly, you know, we could have picked a probability. What's the Z value that gives us, for example, 80% in the lower tail? In other words, cumulative probability of 0.80.
Wait, does the 0.80, is that a probability or is that a value?
Oh, that's the standard score, isn't it? I wanted to give a probability, didn't I? I said I was going to give a probability. It's got to be in there. There, 0.80. There's the probability. What gives us 80% is the cumulative probability. It is 0.84162. And you can work out others. 0.90 is a common number to ask, or 0.90, 1.28, 0.95 is another common one, and there's reasons why. That's 5% in the upper tail, and often we want 90% in the middle, which is 5% in each tail, and that would give us 1.6449. Or an extra decimal place there. Okay, so you can use that, but it also allows you to change the mean and standard deviation. So for the questions we worked out the other day with a mean of 60 and a standard deviation of 10, let's just take that out. And we'll take this out, and so our first question, what was the probability x is greater than 65? Well, to get the probability x is greater than 65, we first of all had to work out the probability x is less than 65. So we put 65 in there.
Wait, but do we put it in the probability box? Or?
Oops, did I get it in the wrong box? I did. I put it in the wrong box. This thing... yes, let's make sure I get in the right box. 65. So what's the probability less than 65? 0.69146. So when we subtract that from 1, that's where we got our 0.3085. We also asked for the probability less than 45. And we wanted that one. And that was we had 0.0668 using our table. An extra decimal place. This one gives us 0.0668.
So Gary,
one.
I have a question.
Yes.
If you were working on the homework problems and you wanted to check your answer, would this be useful?
Oh man, you could check your homework answers so fast. So this is part of the idea. Is what you can do. What you do is you fill in any 3 boxes, and it can calculate the 4th box. Okay, and you've got a problem or two there that one of those mean or standard deviation boxes might be the one you want to solve.
I have a follow-up question.
Yeah.
Can you use the calculator on the exam?
Can you use this calculator on the exam?
Yeah.
No, you cannot.
Okay, also good to know.
That's good to know. So, you can check your homework, but you don't want to depend on this for actually answering the homework, right? You want to be able to do the hand stuff, hand calculations, work with your table, and but this is an easy way to double check your work, right? So it's very cool. It's very cool, and you know, you could try doing a couple things where you, well, let's just suppose we did this one. Suppose we had the probability less than 45 was not what we had there, but maybe it was 0.20. And if the standard deviation was 10, it'll tell us that the mean of that distribution was 53.4. Or I could put a mean in there. Maybe I gave it a mean of, I don't know, 58. And if it was a mean of 58, what would be the standard deviation that had that probability of 0.2 being under 45, if the mean was 58, and it would come back and say that standard deviation had to be about 15.45. Okay, so you fill in 3 of the boxes, it'll tell you what the value is for the 4th. So that's kind of nice thing to work with. Okay, so that's enough on that thing, and now I'm going to try to go back to my slideshow and hope that I haven't broke everything.
While Gary's doing that, in Mathematize, I'm going to say, what is the probability that Gary will get it to work? You guys tell me. Not actually. Okay, go ahead.
Okay.
Wait, did it just work?
It seems to
It's a
have.
miracle.
Okay. So this is up in your pre-post, so you know, don't bother writing this out. And I will be putting up slides after this where I replace the pre-post with a couple extra things here, one small correction. So using R, there's 4 key functions here. We call them P norm, Q norm, D norm, and R norm. And we used 3 of these with the binomial distribution, but we didn't really work with a D binom. There is a D binom, but it's a little hard to interpret. So what we want to do is investigate what each of these things do. And right off the start, we'll just mention that just like the binomial distribution, the P function, where we did a P binom before, but we now have a P norm, it returns a cumulative probability. In other words, the probability x is less than or equal to x for a normal distribution with any given mean and standard deviation. Now, if you don't specify the mean and standard deviation, it will take it as standard normal, 0, 1. Okay, so we'll just check that one out. Now, the Q norm function takes a cumulative probability and it returns what the value of x will be for which the probability x is less than or equal to little x. So I guess that should have been a little x in there, wouldn't you agree?
It's not a little x?
That should be a little x. Little x. That should be a little x. Gives you that probability. And then we'll ask what does the D norm do and what does R norm do? So the R norm we'll mention is in fact a random number, a random variate generator, and it's kind of cool. And then we'll just ask what does that D norm do? And well, there's a reason it's called D norm. It is the value of the density function at that value of x. So let's kind of take a look at how this is going to work. And now comes my dangerous thing is I'm frightened. I'm going to exit. I'm going to exit, and I am going to bring up an R window. Actually, I can bring up any R window. It doesn't matter which R window I bring up. What was I working? I was working out, just some random numbers here. Okay. Well, I was working out a couple numbers, but nothing important. Okay, so let's just bring up this R window right here, and let's just get that out of the way. Okay. So what did we say? We had P norm. Let's try P norm. of 1.96. I'm picking these values because these are values that people tend to, after a while, you just tend to remember them. And if this works right, and I haven't broken anything, I should get 0.975. Oh, look at this. It's got a little bit of extra juice on the end, the 0021. But the 3 decimal places, yes, 0.975. Okay, so what we've done is the p-norm is cumulative probability. Now, let's try a q-norm. So a q-norm, well, let's work with the one that we know. Suppose, oops, where did that 9 go? 0. So, am I hitting that? Yes, 0.975, but I'm not going to ask for p-norm. I'm going to ask for q-norm. Q-norm. Yes. And that comes back with 1.96, but in fact to more decimal places, so it's 1.959964. That's what we rounded off to 1.96. Okay, so again, any questions on the difference there between the p-norm and the q-norm? Okay, so now let's ask, what does d-norm give us? Well, it takes a value of x, and let's take the 1.96 here again, and ask for d-norm of 1.96, and that's 0.05844,094. What the heck has that told us? What has that told us? Well, let's try d-norm of 0 first of all. 0.3989. Okay? So, what that tells us, if I can move to the dock camera for a second. My goodness. There's my nice clean paper. My paper is all written all over. Okay, I can work with this one anyhow. Back to this one. Okay. Gotta use the back of my paper. Okay. There was my standard normal distribution. Mean is 0. What this is telling us, at 0, the value of the density function is 0.3989423. And when we went to 1.96, which is about 2 standard deviations out, about here, this was 1.96. This area in here was 0.975, consisting of 0.5 on this side and 0.475 on that side. So we had 0.025 in that tail, but the 0.05844, where was that? That was right here. That was the height of the curve right there. 0.05844,094. Okay, so d-norm simply gives you the height of the density curve, and it's simply scaled so that the total area under the curve is equal to 1. Okay, is it useful to you? In most situations, no. The ones that you're going to use are the p-norm and the q-norm. Okay, either get me a cumulative probability or find me the value of z or x that gives me, that has a certain particular cumulative probability. Any questions about those ones right now? Okay, so again, just tighten the curve, and this gets maximized here. And again, just emphasizing, you do not calculate a normal probability by plugging x into the density function. We've got to get the area under the curve. Okay, so I'm up here, and now what else can I do? Well, let's just face it, random numbers are always fun.
Wait, I have a question here. You figured out this special number, 0.3989, which is the height of the curve.
Right.
What would happen if you did the reciprocal? Would that be anything interesting? Can we do that? 1 divided by that?
You want 1 divided by that?
Yeah, I want 1 divided by that.
Okay.
1 divided by. And actually, I want 1 divided by it squared. I'm feeling crazy today.
You are just a wild man.
1 divided by it squared. Can't stop me.
Yeah, no, absolutely.
6.283. Is that a special number? Does anybody recognize 6.283? All right, divide it by 2 for them, please.
Pardon?
But I want 1 over d norm squared divided by 2.
You want 1 over d norm? Well, this man, he is so demanding. He is so demanding. $3.141593. Is that a special number? Does anyone recognize that number? Put your hand up if you recognize that number. All right, amazing. It's pi. All right. So wait a second. The pi was in the curve the whole time? It was it. We saw the density function. We had
All
pi.
right.
We had the root of 2. We had e.
Look at that. Yeah. All right. There's
Like, I just find that so freaky.
it's very eerie. Yes.
It
All
is
you have to
eerie.
do is torture it a little bit, and pi comes out. Okay. Great.
Okay, that's so cool. Okay. Oh, before I go to generate some random numbers, I want to just take a look at a couple of these. We had a couple problems again, and so we wanted the probability x is greater than 65 with a mean of 60, standard deviation of 10. So I could have done, let's see, what could I have done? What could I have done? I needed to get a probability. A probability was p norm. And then I said, I want it greater than 65, so I'm going to put 65 in there. And then I'm going to put the mean and the standard deviation. So the mean is 60, and that's the standard deviation is 10. And what that's going to give us, well, first of all, it's not going to give us the right thing, so let's just do that, because this is going to give us the lower tail probability, what we call the lower tail probability or cumulative probability. But if I just take that and subtract that from 1, we got our answer, our 0.3085. Okay, and well, how about this question right here? We wanted the value of x naught such that the probability above x naught was 0.90, and okay, so there's a couple ways to go about doing that, but let's just work with one of them. And so now I'm going to do the Q norm, and I'm going to work with but now I put a probability in. I want a cumulative probability. So if my area above x naught is 0.90, my area below x naught was 0.10. I'm just going to put that in directly, and then it's going to hopefully give me 47.2, which it did, but with great precision. 47.2. We had 47.2 rounded to 1 decimal place. They have the same thing, 47.18446. or 448. Okay, so we did a bunch of P norms, Q norms. Let's take a look at some R norms. R norms. R norms. What's an R norm? Okay. So one thing I like to think about is, mean of 60, standard deviation of 10. What's a realistic population that could have a mean of 60, standard deviation of 10? Sheep. Kilograms in kilograms. Big population of sheep in kilograms.
You guys remember last time you picked up a sheep? Like it was like about 60 kilograms, right?
Above 60 kilograms. You got
Some are lighter,
it depends
some are
on the
heavier.
breed. Depends on the breed. You got to kind of go around, weigh some sheep, heft them up. Okay. So if we wanted to simulate some sheep, 10 sheep. Give me 10 sheep. Mean 60, standard deviation 10, and there it is. There's our 10 sheep. There's the weights of the 10 sheep. Okay, so that's kind of cool. You could generate those, and you could generate a lot more sheep. Now, I want to be careful here, because you see, if I generate that again, I get different numbers, and so it's just safe to.
Is there a question in the middle?
Pardon?
There's a question.
Oh,
Yeah, so since it's continuous, it's like a zero probability to get any one value, but then this function grabs values. So is it that we can't assign a probability to it? But this is
so what it's doing is telling you what is the value. It's randomly selecting a probability between 0 and 1 as its cumulative probability, and then it's putting that cumulative probability into the I gotta be careful here, into the Q norm function, and that returns an X value.
But another way to answer the question is that you'll notice it only has 5 decimal places. So you should think of this as like it's 40.12666. If you wanted infinitely many decimal places, it's a probability 0 event. This number actually stands for a whole interval of the real line, which is 40.1266660 all the way up to 40.12666999999. And that little tiny interval on the real line has some super microscopic probability to get chosen. But when you get this number to 5 decimal places, you're saying it's somewhere in that region on the decimals I can't see. So it's true, any individual actual real number has 0 probability. This to 5 decimal places represents like a tiny range of sliver of many real numbers. And so this, the probability it starts with 40.12666 is not a probability 0 event, even though any specific actual number is probability 0. So that's maybe the philosophical resolution you're looking for. Gary was telling you how the computer actually does it under the hood. It just generates a random number to some number of decimal places and then feeds it into a function.
Okay, last thing I'm going to do today is just generate
100 sheep.
100,000 of them.
No, don't. We can't. They won't fit.
100,000 sheep, all in this room. But I've got them assigned to X1, so we won't see them. We don't want to see them because it'll
they're
keep
ghost
going
sheep.
forever. Okay? But we're just going to do a histogram of X1. And there it is, or I could add some breaks. I could add breaks. Do 200 breaks, so it's got little tiny steps. And look at that. That's what was generated. That's our 100,000 observations generated randomly according to the normal distribution. So we have a very nice pile of sheep, and they are pretty close to normally distributed.
This sheep over here is like 100 kilograms. It's a big sheep.
That is a very big sheep, but it's a rare thing to get one that big, right? Anyhow, that's it for today, people. Have a great weekend.
Don't forget you have a homework assignment due next Friday. So I don't know if you want to start it now.
Yeah.